Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I would like to discuss a little bit about a phenomenon and a problem that appears in operational amplifiers and that, sometimes we need to take care of. Not always. Actually, this is the kind of problem that we can ignore most of the times, but sometimes we just don't have the luxury of ignoring. The problem is that any operational amplifier has some input capacitance associated with it. This is due to all sorts of construction details. You know, the fact that an op-amp is a circuit with several metal terminals, metal pins, right, that are parallel to each other and that go inside a plastic package. As we all know, when we have two electric conductors separated by an isolator, then we have a capacitor formed. So this parasitic capacitance manifests itself on the input of the op-amp, and they are a problem most of the times when we are having a very high input impedance, as well as when we want to work with high frequencies. Then this input capacitance becomes a problem. So let's dive into the problem and let's explain what we have and how to measure and why this whole video surrounding this problem. Long story short, I need some differential probes for my oscilloscopes and I do not want to buy them. The cheapest ones cost about $300 a piece. I need more than one. I don't have the money, and even if I would have the money, by spending, I don't know, $300 on just a single, very cheap, very, low quality differential probe seems just way too much. So I decided to design my own differential probes and build my own. I'm not 100% there yet. I know how to build one, but I haven't finished the entire design and actually built it. When I will come back on YouTube with another video and I will present to you everything, the schematics, the way it works and everything involved. However, when designing such a thing, we come across this problem of input parasitic capacitance of the op-amp, and we need to take care of it somehow. First of all, we need to understand it. Second, we need to know how big these capacitances are, and then we can know what to do about it. And here's where the more subtle problem appears, and hence my desire to make this video. For some op-amps, we might have this parasitic capacitance written in the datasheet. Okay, so for example, if we are taking a look, sorry, this has a tendency of just zooming in on a single click. If we take a look at MCP 651 or 23459, there's an entire family of microchip technology operational amplifiers. I'm just giving these as an example, okay? Don't cling on them because a whole bunch of other op-amps have this information written in the datasheet. I'm just giving this model or this family of model as an example. If we take a look in the datasheet of this family of op-amps, at some place in the third page we see at input current and impedance group, we see a couple of specifications for common mode input impedance and differential input impedance. Now, technically speaking, impedance is one thing, capacitance is another thing. However, if we take a look closer at what they tell us about these two impedances, well, we see that the value is expressed in something in parallel with something else. And if we take a look at units column, we see ohms in parallel with picofarads. Well, that clearly tells us that, okay, the impedance is indeed 10 to the power of 13, which is a very, very big, like I think 10 tera ohms. If I, the power of 3 is kilo, power of 6 is mega, the power of 9 is giga, and the power of 12 is tera. Yeah, so 10 to the power of 13 is the equivalent of 10 tera ohms. However, the interesting thing here is that parallel with 9 and parallel with 2 picofarad part. And they don't specifically tell us that, hey, we're not giving you just the impedance, we're also giving you the capacitance. They basically let us figure this by just looking at the datasheet. And of course, we need to know this firsthand. We need to be knowledgeable enough to recognize that they are giving us both the impedance and the capacitance. This is nice. However, in the case of other operational amplifiers like Tele 074, 072, 071, or other similar operational amplifiers that are older, well, they don't really give us that information at all. First of all, we see only an input resistance, and that's it. Okay, so whereas in certain OpAmps datasheet, we see common mode and differential mode impedances separated. For these older OpAmps, we only see input resistance, and that's it. We don't know it's common mode, it's differential mode. They didn't bother to tell us. It is true that it's still very, very high. It's 10 to the power of 12, so 1 tera ohm is way, way, way above whatever we might have a problem with. However, from the perspective of the capacitance, we know nothing, absolutely nothing. We're pretty much like Jon Snow, we really don't know anything about the capacitance. Well, that's a problem, because if we want to use such an op-amp, in a circuit that has very high input impedance and that needs to work with relatively high frequencies, then the input capacitance will affect this circuit. And even though they don't specify the input capacitance, it is there. Okay, so I don't make any mistake of thinking that if this is not written in the datasheet, it means that it does not exist. No, it does exist. It's just that they didn't bother to measure it and to express it in the datasheet. Okay, so we have to do something to figure this, to find this capacitance on our own, so that we can, compensate for it. Hence the need for this video that I'm presenting to you right now. Ignore whatever you see written in Romanian, it doesn't matter, it's from the video that I made in Romanian. I'm just gonna explain everything in English, everything that you need to know, so just ignore whatever you don't understand written with words. So the first thing that we need to conceptualize, that we need to do, is to conceptualize where are these parasitic capacitances, and because basically we need to know how they affect the op-amp and therefore the rest of the circuit. And if we search on the internet, we find a couple of articles, at least a couple of articles. I haven't seen any video made on this topic, so I'm making it myself. I'm making one myself right now. But we see a couple of articles that explain that these capacitances are found here, like this. So we have a differential mode capacitance between the two inputs of the op-amp, the non-inverting and the inverting one. And we have a couple of common mode parasitic capacitances between the ground of the circuit, whichever it is, and each input. So we basically have a common mode capacitance between the non-inverting and the ground, non-inverting input and the ground, and we have another common mode capacitance between the inverting input and the ground. Now, the ground can be the negative power rail for some op-amps, it can be halfway between the negative and the positive. It doesn't really matter, to be honest, because if we combine it with the internal resistance of whatever power supply we use to power this op-amp, that internal resistance is considerably smaller than anything else. So it kind of acts like a short circuit. So yeah, so we can just conceptualize ground just like that, and it doesn't really matter what ground it is. Okay. Now, in case you don't understand why these input capacitances matter and why this is a problem, and by the way, these parasitic capacitances are in the order of picofarads, maybe worst case scenario tens of picofarads, but they are very, very small. And the first thought that we might have is, you know, well, if they are so small, then why do we even bother with them? Well, because when we have a very high output impedance from the previous circuit that feeds signal into this circuit, then we basically have an RC filter. What's it called? The kind of filter that low pass filter, the kind of filter that cuts higher frequencies than a certain frequency and allows only lower frequencies. And this is a problem. This can be a serious problem, you know, because let's say that the output impedance of the previous circuit is I don't know, 1 megohm. Okay, you should have known by now, you should have watched a video, I haven't made it, but there are plenty on YouTube, a video regarding RC filters. So basically filters made by resistors and capacitors. You have, in an RC filter, just as a reminder, you have the frequency, the cutting frequency, well, the corner frequency from which the filter starts to work. And in the case of a low pass filter, it starts to cut frequencies above this. You have the frequency defined as a mathematical formula by the formula of 1 over 2 PRC. Okay, so basically this gives us the frequency, and if we calculate, if we let's say we have 1 picofarad, a very low parasitic capacitance, 1 picofarad on the input of an op-amp, but we have a very high output impedance from the other circuit that feeds signal into this one. Well, the frequency, the cutting frequency is going to be 1 over 2p multiplied by, let's say, I don't know, let's say 1 megohm, so 1 million, multiplied by the capacitance, which is, I said 1 picofarad, so milli, micro, nano, pico, okay? And we have the result is going to be 160 kilohertz. Well, that's a problem. Or, well, in some cases it's not a problem, but in other cases it can be a problem. So basically every frequency above 160 kilohertz, when we have 1 picofarad of parasitic capacitance and 1 megohm output impedance from the other circuit, we have frequencies that above 160 kilohertz are cut, are attenuated by, you know, 20 decibels per octave, per decade, sorry, not per octave, per decade, and that's a problem. Okay, I'm trying to build, in this case we are trying to build differential mode, a differential probe that can work up to the maximum frequency of the op-amp that's being used. I decided to use TL074, and this is said to be able to work up to 3 megahertz. Okay, well, if I don't take care of these capacitances on the input, then my frequency is not going to reach anywhere near 3 megahertz. Okay, again, according to the formula, everything above 160 kilohertz is going to be attenuated drastically the more we increase the frequency. And this is provided that all of these parasitic capacitances are 1 picofarad and the impedance is 1 megohm. However, in my case, I'm going to have 4 megohms of impedance, and the capacitance is going to be bigger, because the real parasitic capacitance of the TL077 op-amp is bigger. Okay, so needless to say, we need to find out these parasitic capacitances for the op-amp that we are using if we do not know them from the datasheet. Okay, it's important. So understanding the problem, now we can think of a few experiments that we could do in order to determine these capacitances. And basically, in essence, we need to plot a frequency response analysis, or sometimes called Bode plot. Okay, we need to basically exploit the fact that by using a certain high value resistor, we are getting an RC low pass filter, and by essentially sweeping a number of frequencies, a signal that starts with a certain frequency and goes up to another higher frequency, we can see the level of attenuation at various frequencies, and based on that we can calculate in reverse this capacitance based on the frequency and the impedance that we have. Okay, so first things first, since we are going to use, I needed to use a more advanced oscilloscope that has this this feature. So I used an MDO, mixed domain oscilloscope, that has also a frequency response analysis tool in its software. Now we are going to use the inputs of the oscilloscope, and well, those have their own input capacitances, which are going to be affecting our experiment. So the absolute first experiment that we need to have is to determine what is the actual input capacitance of the oscilloscope. Okay, at least the one that we are seeing in our experiment. Because for me, for example, I have an oscilloscope that has a 16 picofarad capacitance on the input written on the front panel of the oscilloscope, so theoretically we should be able to count on it. However, in practice, the reality is that overall I have experienced a much higher input capacitance. Okay, and this is due to a number of factors. I didn't bother to, you know, take a look at why do I have more. It doesn't really matter. What matters is that we need to determine what this capacitance is. So the first experiment that we have to do is basically by taking a 1 megohm resistor, which is the same as the 1 megohm input impedance of the oscilloscope, placing it in series with the input. In this way we're basically creating a voltage divider that attenuates at half the input signal. And because we also have this capacitance, this attenuation is not going to be constant throughout the entire spectrum of frequencies. This actually will get bigger and bigger the higher the frequency will go. So we are setting up the signal generator of the oscilloscope for some frequencies. We are monitoring this signal directly through the first channel, and the second channel, like I said, is placed in series with this 1 megohm input resistor. In my case, it was a 995 kilo ohm one. I actually measured it to know precisely its value. It doesn't matter all that much. Anyway, and we're going to basically plot the frequency response in order for us to figure what's this real capacitance of the oscilloscope, okay? And this is the frequency response with blue. The baseline level is at -6 decibels because we have basically halved our signal generator's amplitude. Okay, when we're halving some signal, that's the equivalent of a -6 decibel attenuation. And the corner frequency determined by the formula that I've just shown you earlier is the one where we have a -3 decibel attenuation from the baseline. So in this case, -6 -3 equals -9. So by looking at where -9 decibel is and drawing a horizontal line that intersects our frequency response curve, the one in blue, okay, we ignore the one in red, that's the phase curve, we don't care about the phase, we just take a look at the one in blue. Then we see the frequency, which is somewhere between 2 and 3 kilohertz, something like that. And by performing the inverse formula, we can basically calculate the capacitance as 1/2 PFR, okay? We've just we know the resistance because it's 1 megohm. We have determined the frequency, so therefore we can determine the actual capacitance, which for me was around 59 picofarads, okay? So these 59 picofarads are going to further influence every other experiment that we are going to do, okay? This was necessary to determine precisely this capacitance, because otherwise, if we would take into consideration only the theoretical one written on the front panel, we would get wrong results and wrong calculations, right? The difference between 16 and almost 60 is quite big, okay? So now that we know the actual input capacitance of the oscilloscope, again, I'm simplifying this thing. Of course, it's not just the oscilloscope, it's everything with, you know, probes and everything involved. Now we can actually get to work and perform several experiments in order to actually visualize our problem with the OpAmp. Because remember, we are trying to determine the parasitic capacitances of the OpAmp, okay? So the first thing that we do is to make sure that we know how far, in terms of frequency, how far the OpAmp can go on its own, given that the input impedance is very small and that therefore the parasitic capacitances don't matter. And for that we just take an OpAmp, we power it from a ±12 volt differential voltage, right? We make it as a buffer, so we tie its output to the negative input, to the inverting input, and we basically run the same frequency response analysis by looking at on channel 1 of the oscilloscope on its input, where the signal from the signal generator comes from, and with channel 2 we monitor the output, and normally we shouldn't see any problem whatsoever. And this is exactly what we have here. As a reminder, like I've shown you, the unity gain bandwidth for this TL07 something is said to be 3 megahertz. And yes, this is indeed about 3 megahertz. It's actually a bit more. We see that slightly below 1 megahertz we experience some form of amplification. I don't really understand why, but I don't care all that much. We see that it goes up to 3 megahertz, and then from 3 megahertz 3 megahertz down to 4 megahertz it starts to have some attenuation. It goes down to 0, and from there it keeps attenuating and so on. Okay, so yes, this is a proof that indeed my Tele 070 something is workable up until 3 megahertz, more or less. Okay, so now we have to make it so that the input capacitance starts to reveal itself, starts to basically influence the results. So we have the exact same circuit in experiment 2, except exactly before the non-inverting input we are placing a 1 mega ohm resistor. Okay, and now is when these parasitic capacitances start to form a low pass filter with this input resistor. We are monitoring with channel 1 the signal from the signal generator, the one before the input resistor. Okay, it's very important. We are not monitoring the one after, because then we won't be seeing any attenuation at all. And well, the results of the second experiment kind of speak from themselves. So if in the first experiment we saw that we can go up to 3 megahertz or even higher, in this second experiment we see that starting from about 20 kilohertz we have the familiar curve of the low pass filter. Okay, this clearly shows us that yes, there are some parasitic capacitances there, and yes, they are affecting greatly our circuit. Now, if we calculate, you know, with a reverse formula, 20 kilohertz and 1 mega ohm, we basically get a total parasitic capacitance here of 8 picofarads. That's okay-ish. I mean, now we know around where we are. But we kind of still want to basically figure the differential mode and the common mode capacitances separately. So we need to do other experiments. And for this I have experiments 3, 4, 5 that I'm going to show you in a moment. In these first two experiments we cared about the output signal of the OpAmp. However, in the next experiments we won't care at all about what the OpAmp spits on the output. We will only care about monitoring the inputs. So in experiments number 3 we get to have the first channel of the oscilloscope monitor the input signal. The input signal is also fed through a 1 mega ohm resistor. However, it is fed to both inputs of the OpAmp. So we tie both inputs of the OpAmp together, and with the second channel we are monitoring the signal that we get here, that we see here. The idea is that by short-circuiting these two inputs, we are essentially getting rid of the differential mode capacitance, and we only have both common mode capacitances placed together in parallel, and therefore we have two values, it's like placing two capacitors in parallel. Okay, you get the double capacitances. Okay, so the results for this third experiment are these ones. We see that the frequency has the cutting frequency has gone down a bit. We have it somewhere between 2 and 3 kilohertz. I said around 2.4 kilohertz. approximately. I also tried to draw a tangent to this entire curve. Ignore it. I failed to draw it, you know, accurately enough. But the results are good enough because, you know, we can have some calculations done based on this result, because here we know that we have a total capacitance made out of two common mode capacitances plus the oscilloscope input capacitance, right? Because remember, each channel of the oscilloscope has that input capacitance that we measured earlier, and that of course affects, you know, the results of our experiments. Channel 1 doesn't matter, but channel 2 does matter, because channel 2 experiences the very high input impedance. Okay, so basically the a single common mode capacitance is half the difference between the total capacitance and the oscilloscope capacitance. The total capacitance can be calculated with the aforementioned formula and with the frequency that we observe here plus the value of this resistor. I've calculated it to be 67 picofarads, and therefore if I perform the calculations here, I get that the common mode parasitic capacitance is around 4 picofarad. Okay, good enough. And now we want to see the differential mode capacitance. So for that we make a fourth experiment, and we are where we are taking the inverting input and we are tying it to the ground. Okay, the signal gets through a 1 megohm resistor into the non-inverting input only, and that's what we are monitoring with the second channel of the oscilloscope. Basically, when we take the minus input and we are tying it to the ground, we are short-circuiting one of the common mode capacitances, and we are placing the other common mode capacitance in parallel with the differential mode capacitance. Okay, now we know the common mode capacitance from the previous experiment, so we therefore can calculate the differential mode capacitance. So where was it? Yeah, experiment 4. So I am okay, this is the frequency response of the fourth experiment. We see that it's very similar to the previous experiment. However, the frequency, the corner frequency of this RC filter is slightly higher. I would say 2.5 kilohertz, just slightly higher. So by calculating in reverse, we get a total capacitance of 64 picofarads, which is made by one common mode plus one differential mode plus the oscilloscope input capacitance. So if we, you know, make some differences here, we get that the differential mode capacitance is around 1 picofarads. So now we have both parasitic capacitances measured, and now you know exactly how to proceed if you have an op-amp for which the parasitic capacitance is significant, is important, but you don't know it, right? And I've also made a fifth experiment where I basically left the input, the inverting input, not connected to anything, so that I would have all three of these parasitic capacitances come into play. But of course the differences aren't big enough, because when you have a very small capacitance like the differential capacitance in series with a very big capacitance, then the big capacitance will almost not matter at all. Okay, but I just did it anyway just to see the results, and here we have the results. Basically they are almost identical, and at least in terms of the corner frequency, almost identical to the previous experiment. Okay, I'm flipping between 4 and 5 now, so you can see the differences. Again, ignore the red line, it's the phase, and it has different scales for these two experiments. the gain with the blue is essentially the same. Okay, so that's it. It's not a big, it's not rocket science. It's not a big philosophy, but nevertheless, it's something that sometimes we need to bother with. And when we don't have informations come in handy in the datasheet, we need to perform some experiments to, obtain those informations for ourselves. So I hope you now understand how to perform this task whenever you need it. Thanks a lot for watching my video. Please like and subscribe to the channel if you've enjoyed this video. I will definitely do more in the future. Also, if you would like to support my channel, you have a Patreon link in the description. Your help is very much appreciated. By helping me financially to buy more components and more lab devices, I am able to learn faster and come here to you and teach you as well, so that you don't have to bother wasting so much time and energy as I am wasting learning these things. Thanks a lot for watching. I'll see you next time in the next video. Bye bye.